What specific problem does your proposed AI agent aim to solve in computational notebooks, and what existing challenges does it address in terms of error resolution?
The proposed AI agent aims to solve the problem of error resolution in computational notebooks, which are plagued by low reproducibility rates and high code entanglement, leading to a significant number of errors. Specifically, it addresses the challenge that after a rerun, notebooks only achieve the same results with a 4% probability, and 75% cannot be executed without exceptions. The agent is designed to interact iteratively with the notebook environment, utilizing runtime information to resolve errors effectively, which is difficult for existing models due to the stateful nature of notebooks. By integrating the AI agent into Datalore, it can create, edit, and execute cells, thereby facilitating a more natural and efficient workflow for developers. This approach not only enhances the error resolution capabilities, but also aims to reduce the debugging distractions that developers face, ultimately improving their productivity.
How does the proposed AI agent work? Illustrate its operation step by step, detailing the interaction between the agent, the LLM, and the notebook environment.
The proposed AI agent operates through a structured interaction between the agent, the LLM, GPT-40613, and the notebook environment. Initially, when an error occurs in a notebook cell, the environment sends the error stack trace and the corresponding cell source to the agent. The agent, acting as a stateful back-end service, utilizes a memory stack to store the interaction history and prompts the LLM with this history, along with observations from the environment. The LLM then generates a prediction for the next action, which the agent converts into a tool call, e.g., creating, editing, or executing cells, and sends back to the environment. The environment executes the proposed action and returns the output as an observation, allowing the agent to reflect on the outcome and decide on the next step, continuing this iterative process until the error is resolved, the maximum iterations are reached, or the response timeout is exceeded.
Can you provide a practical example of how the AI agent resolves an error in a computational notebook? Walk through this example, detailing each step the agent takes and the tools it uses during the process.
In the proposed system, when an error occurs in a computational notebook, the environment sends the error stack trace along with the corresponding cell number and the source code of the notebook cells to the AI agent. For instance, if a user encounters a runtime exception in a Python cell, the agent first receives this information and initiates its workflow. The agent then utilizes its tools, such as creating, editing, and executing cells, to address the error. The agent reflects on the previous actions and observations to determine the next step, which may involve editing the problematic cell to correct the code or executing a new cell to test a potential fix. If the agent successfully resolves the error, the cell executes without exceptions, and the agent can then choose to finish its process or continue exploring further if needed. Throughout this interaction, the agent communicates its actions and reasoning to the user via a chat interface, providing transparency in its error resolution process.
What are the theoretical or practical advantages of using your LLM-based AI agent compared to the existing single-action solution in Datalore for error resolution?
The LLM-based AI agent offers several theoretical and practical advantages over the existing single-action solution in Datalore for error resolution. Firstly, the AI agent utilizes an iterative approach, allowing it to conduct multiple actions and adapt based on feedback, which enhances its ability to resolve complex errors effectively, as evidenced by a higher user perception of its error resolution capabilities, mean value of 4.03 for the AI agent compared to 3.41 for the single-action solution. Secondly, the agent can create, edit, and execute cells, providing a more interactive and flexible environment for developers, which aligns with the natural workflow of data science tasks. Additionally, the AI agent's design incorporates a memory stack that retains interaction history, enabling it to reflect on previous actions and improve its decision-making process, unlike the single-action solution that operates on a single-step basis. Finally, while the AI agent incurs higher costs due to increased token consumption, its ability to resolve errors in a more comprehensive manner justifies this expense, making it a valuable tool for developers seeking to enhance their productivity and efficiency in computational notebooks.
How was your method validated? Describe the experimental design, datasets used, and metrics for evaluating performance, particularly how you ensured that the agent did not employ prohibited hacks during error resolution.
Our method was validated through a comprehensive evaluation that included both system performance and user experience assessments. We utilized a dataset of fine-grained Jupyter Notebook execution logs, which encompassed over 100 hours of logs capturing all cell additions, executions, and deletions during data science tasks in a hackathon, allowing us to reproduce real errors for testing. The evaluation metrics focused on whether the agent successfully resolved errors, defined as a cell executing without exceptions post-resolution, and we manually checked the error resolution logs to ensure that the agent did not employ any prohibited hacks, such as deleting error-causing code cells. Additionally, we conducted a user study with two groups of participants, one using the AI agent and the other using a single-action solution, to measure subjective productivity and satisfaction, employing a System Usability Scale (SUS) for qualitative analysis. This dual approach ensured a robust validation of the agent's capabilities while maintaining adherence to the defined operational guidelines.
What main findings or results did your AI agent achieve in the user study, specifically regarding developers' subjective productivity and satisfaction? How did these results compare to the single-action system?
In the user study, developers using the AI agent reported a more positive perception of its error resolution capabilities, with a mean score of 4.03 compared to 3.41 for the single-action system, indicating that participants found the AI agent more effective in resolving errors. However, while both systems received high ratings for positive productivity feedback, the AI agent scored slightly lower in terms of ease of use and mental effort, with participants noting it was mentally harder to interact with compared to the simpler solution. The average score for positive productivity feedback was 4.08 for the AI agent and 4.10 for the single-action system, suggesting comparable effectiveness, but a preference for the single-action system in terms of user experience. Additionally, the AI agent received a higher average score for negative productivity feedback, 1.57, compared to the single-action system, 1.31, indicating that users found the AI agent more complex and cumbersome to use. Overall, while the AI agent demonstrated superior error resolution capabilities, it faced challenges in user interface design and user control, impacting developers' subjective productivity and satisfaction.